Good afternoon, everybody, and thanks for coming to this seminar. Today's speaker is Dr. Helena Domínguez Sánchez from the Institute of Space Sciences in Barcelona. She will talk about deep learning algorithms for the morphological classification of galaxies. For us, it's a pleasure to have Helena as one of the invited speakers of the Institute of Cosmos Science Colloquia. She's one of the promising talents of the astrophysics of this country. She's an expert in the field of galaxy formation and evolution, where she has specialized in exploiting large astronomical data sets over a wide range of wavelengths, in particular by applying big data and artificial intelligence techniques. Today's talk is an example of this strand of her work. All this with the aim of understanding how and why the properties of galaxies have changed across the history of the universe. In spite of her youth, she already has an extensive international experience. She got her PhD at the Universitat Complutense of Madrid, but all her postgraduate work was developed at and supervised by professors of the Observatorio Astronomico di Bologna in Italy. Afterwards, she carried out several postdocs, first at the Instituto de Astrofísica de Canarias. Then she returned to the Universidad Complutense de Madrid for 3 years with another postdoc. And after that, she went abroad again to spend another 3 years with a joint postdoctoral position at the University of Pennsylvania and the Observatory of Paris, working with Mariangela Bernardi and Marc Huertas Company, among others. She has been also a visitor to several top-notch research institutions, such as the European Space Agency Center, the National Astronomical Observatories of the Chinese Academy of Sciences, the University of California, Santa Cruz, or the CIEMAT in Madrid. And as previously noted, she has since last year a permanent position at the Instituto de Ciencias del Espacio, which, as you know, yes.
No, sorry to interrupt.
It's not permanent?
It's not permanent.
Okay,
I wish,
well,
but I have to
she won a
position
in the, or is member, okay, or is a staff, then, sorry about that, of the Instituto de Ciencias del Espacio, which, as you know, is part of the Spanish National Research Council and the Catalan Institute for Space Sciences, okay? At the ICE, she has her own research group, and she's involved as principal investigator in several projects on galaxy evolution with collaborators from international research institutions, while supervising graduate and PhD students. Finally, let me add that she also keeps a good record of publications in the major peer-reviewed journals of astrophysics and has regularly given invited talks in prestigious academic institutions. To mention some, the Universities of Paris-Saclay, Yale, Shanghai, or the Center for Computational Astrophysics and the Space Science Telescope Institute. Okay, so we are very happy that the researchers of the standing of Dr. Helena Domínguez Sánchez has accepted our invitation, and since her workplace is actually very close to ours, we hope that we can have her visiting in person our institution in a not too distant future when hopefully this COVID-19 pandemic has already become a memory. So Helena, you may begin your talk when you are ready. Thank you.
Thanks a lot, Jose Maria, for this extensive and very nice introduction. It is really my pleasure to present my work to your institute, and I wish I can make it in person very soon to meet all the staff and potential collaborators in person as soon as this pandemic ends, as you said. So I'm going to share my screen so you can all see my presentation. Let me, okay. Can you see it properly?
Yes, yes.
Okay, I've lost my mouse. Give me 1 second. Where is it? Okay, okay. Okay, perfect. No? Okay, here we are. So today I'm going to talk to you about my research related with the use of deep learning algorithms for morphological classification of galaxies. This has been done with the precious help of some collaborators like Marc Huertas Company, Jesus Vega, or Mariangela Bernardi. And the research has taken place mostly in the University of Pennsylvania, and it's now continued in the Institute of Space Sciences, as mentioned before. This is a very simple table of contents. I'm going to divide my talk in 4 parts. In the first introductory part, I'm going to put in context the importance of morphology and the state of the art of how we know that morphology relates to the evolution of galaxies. In the second part, I'm going to introduce the concept of supervised deep learning and how we have applied this very potential tool for classifying, for morphologically classifying galaxies in the Slow and Digital Sky survey and also from the MANGA survey. Then I'm going to move to some of the caveats of the deep learning, supervised deep learning, which is the lack of training data and ways to solve it. For example, the transfer learning. And in my in the last part of the talk, I'm going to show you very promising results about how can we push our classifications to the limit by combining real images and simulations that we have used to construct the morphological catalog for the dark energy survey in what it will be the largest morphological catalog up to date. So since I see that we are not so many participants and this is a Zoom talk, which is difficult to follow the attention for the whole talk, please feel free to participate, to interrupt me, to ask questions so we can make this more vivid and more participative. Okay, so if we're going to assess and determine the morphologies of galaxies, the first thing that we need to know is why do we care about the morphology of galaxies? The fact is that galaxies have a very wide variety of shapes, colors, structures, and so on. And the importance of these shapes or morphologies is that the way the galaxies look like is really related to the stellar populations and mass assembly, and the star formation histories of galaxies and their evolution in morphological transformations have a parallel evolution across cosmic time. If we take a snapshot of the sky, like this image, for example, we see here the great variety of shapes that I mentioned before. We see a very nice spiral bluish galaxy with the spiral arms and some clumpy star formation regions. We see a beautiful galaxy here with a ring. We also see some edge-on galaxies, and this seen edge-on. We also see the roundish elliptical galaxies. There's even a lens ring over here. So what we would like to do is to put order in these images, right? We can do some zoom ins, and here we also have some irregular galaxies, very nice irregular structures. Again, here some beautiful ring. We can see beautiful interactions of galaxies. There are also clusters of galaxies. In summary, there's a lot of shapes that galaxies come on. And what we would like to do is to order the structure of galaxies to understand this order with in relation to the evolution of galaxies. So the first, this is nothing new. This is already known. This was already proposed by Hubble in the 20s in what is known as the Hubble Galaxy Classification Scheme, where you can see that there are these kind of roundish, very smooth ellipsoid-shaped galaxies, which are known as elliptical galaxies or also early type galaxies. Then we also have the spiral galaxies, which move from A, B, and C due to the importance of the bulge and the importance of the spiral arms. So these are bulge-dominated galaxies, while these ones are disk-dominated with more separated spiral arms. And these two sequences are divided because of the presence of a bar over here. And finally, we have also the irregular galaxies where there's not a clear shape. They're just blobby puffy systems. And in between what are known as the early type galaxies and the late type galaxies, we have what are known as the lenticular galaxies, which is an intermediate class, which is also very interesting as my hosts know, and these galaxies have the characteristics of having a bulge and a disk, but no signs of spiral arms. And there are several discussions about the formation of these objects. We can assign a number, so we can quantify these structural parameters and assign a number to each of these classes. And this is one is known as the T-type, and I will talk about this in the second part of the talk. So as I said in my introduction, the morphology is very closely related to the evolution and current stellar content of the galaxies. For example, it is well known that the spiral galaxies are generally low mass galaxies with young stellar populations and ongoing star formation. And this star formation takes place in the spiral arms. And these galaxies have a rotating disks and are rotational supported. On the other hand, the elliptical galaxies are in general much more massive. They present red colors due to the presence of older stellar populations, and their kinematics is dominated by velocity dispersion or random motions. The evolution of such an important parameter such as mass, star formation rate, and morphology is also very well known. Here I present the star formation rate versus mass plane in 3 different redshift beams, and galaxies are color coding according to their Sérsic index, where bluer colors represent the spiral galaxies and redder colors ellipticals. So the first thing we see here is the clear appearance of the main sequence, in the sense that galaxies have star formation rates which are proportional to their mass. And this main sequence evolves with redshift, becoming higher. So galaxies at higher redshift were more efficient at forming stars. But the nice thing about this plot is that you can see how the galaxies which have a proportional star formation rate to their mass, which fall in the main sequence, they all have spiral shapes. They have a spiral morphology. While on the other hand, the galaxies that have elliptical morphologies, they always have lower star formation rate than expected by their mass. These are quenched galaxies that have already stopped forming stars. And we can see the presence of this red cloud over here at redshift as high as 1.5. In this plot, I want to show you how the star formation, how the mass density of galaxies has evolved across cosmic time in different morphological classes. So in the first panel, I present the mass density versus the age of the universe, or redshift, for the whole population. And we can see that at the beginning in the universe, most of the content of the stellar mass was included in irregular galaxies, which then started to being converted into spheroids, disks, or the combination of the two. So for the whole population, there is a mix of these 3 classes. But if we divide the galaxies into star forming and passive, we see how differently these 2 populations behave. And for the star forming, we have the transformation from irregulars to disk. Most of the content of the stellar mass of star forming galaxies is located in disks, while for the galaxies that don't form stars anymore, they are all almost all spheroids, or disks plus spheroids. And this tells us something about the presence of a bulge. Has to be related somehow with the shut off of the star formation. This has been proposed by several simulation works, and also other like, for example, Solotov, and also other papers, in which in simulations there is a compaction and quenching event, which appears very clearly and are very nicely related. For example, what we have is, here I plot the stars and the density of stars and gas. and here just the stars. And you can see that there's a phase prior to compaction where there's a lot of gas and a very deep potential well. So all the material infalls towards the center, and this creates a very, enhances the star formation, creates a very bright star burst. So it transforms all the gas into stars. You can see here all the stars being formed. And the fact is that at some, and this is what is known as a blue nugget because it's very compact and blue star forming. But at some point, the gas reservoir is exhausted. The galaxy cannot accrete more gas and therefore cannot form more stars. And therefore, it quenches, it stops creating stars. So you can see here that the star formation has ceased in the inner part. And what we have is what is known as the red nugget, which is this very compact, very old non-star forming passive galaxies at high redshift. And these passive galaxies are expected to increase a little bit in size across cosmic time due to minor mergers. But this is actually a topic which is still under debate. We don't really understand what are the implications of the morphological transformations with respect to the stellar population. We don't know what is happening first and how each other affect to each other. So understanding how morphology relates to the galaxy properties and in which way they affect the galaxy assembly and evolution is really one of the major challenges of present-day astronomy. And therefore, it is crucial, it's very important to have accurate and large morphological classifications of galaxies. And so this is what my research tries to solve. Okay, so then the question is, how can we classify large samples of galaxies? Well, this is something that traditionally has been done by visual inspection, but as you can imagine, is really tiring and very time consuming. But moreover, with big data surveys, this is going to be totally impossible. So there are things like Galaxy Zoo that I will talk about in 1 minute. And then finally, we have the automatic algorithms, which is the approach that we decided to use. So for those of you who don't know about the Galaxy Zoo project, this is a science citizen project where the users go to a friendly web interface, are shown a set of images, and they are asked a few questions. So by answering these questions, they morphologically classify the galaxies that they see. So the good thing about this is that because it's a lot of people participate, it's relatively fast to classify large samples of galaxies. But because this is due by amateur astronomers or by non-experts, there are some features which are difficult to recognize. For example, very weak bars are difficult to, most of users fail to identify what we know as weak bars. In addition, there can be discordance between different classifications. When there is low agreement between the classifiers, then the classifications become uncertain. But moreover, with the future big data surveys, there's a calculation has been done that to classify the full Euclid survey, 100 years of Galaxy Zoo project would be needed if it's done in the same path and rhythm as so far. So we need to think of alternatives. And this is where the deep learning, and in particular convolutional neural networks, are the answer. They are really useful, they're very successful, and they're relatively simple to use. And I'm going to try to convince you of all these things. First, by introducing you the first paper where we did this work. It's presented in Domínguez Sánchez 2019. And as I said before, this is done in collaboration with Marc Huertas Compañ and Maria Angela Bernardi. But before I go to explain you the details of my research, I want to do a very small introduction about what we what do I mean when I refer to supervised deep learning? Because there's a little bit of confusion about all these words and expressions which are generally used, and I want to put them in context. So deep learning is a subclass of artificial intelligence, and at the same time is a subclass of machine learning. The difference between machine and deep learning is the feature extraction step. In traditional machine learning, you have some inputs from which you want to learn some outputs, and you do that with a series of mathematical operations. But before that, some features need to be extracted, and these features are expected to relate the input with the output. So for example, if one wants to guess the price of a house, the features could be the square meters, the number of room, the neighborhood, etc. Or in the case of galaxy morphologies, we know that morphologies are very much related to colors, masses, or asymmetries. However, if we skip this step, the feature extraction step, this is what is known as deep learning, and the feature extraction is done automatically by the machine itself. And this has two main advantages. First is that you save the time that you need to invest into the feature extraction, the feature calculation, like measuring the asymmetries and so on. But most importantly, or at least as important, you don't have to guess a priori which are these parameters which correlate with your outputs, because the machine is able to identify them in an automatic fashion. And when I talk about supervised, this is because my inputs have some labels which are known a priori. This is what I call as the truth. And I want my model to predict these labels. So the input of my model and the output of my model should be as closer as possible. So even though it seems like very complicated and people don't understand, and you have this in artificial intelligence word saying, oh, this must be something really tricky, the truth is that supervised deep learning is nothing but a very complex mathematical function. But at the end, you have your inputs, which are your matrices X, and you want to find the function which better transforms these inputs into your outputs. And this is done simply by optimizing this function. The thing is that this function is a very complicated function, and there are a lot of free parameters taken into place. So this is very computationally expensive. And we need to use things like gradient descent to optimize the function in an efficient way. And therefore, it requires a lot of computing power, and in particular, the use of GPUs to be able to do all these tensor calculations in an effective way. So let me specify a little bit how our deep learning models work. We use what is known as convolutional neural network. And in our case, since we want to learn the galaxy morphologies, the input of the model are the 3 color band images. In this case, we use 69 times 69 pixel images, to which we apply all this series of transformation. Here, this is a little bit too technical, but I want to go just a little bit with a brief explanation, but if you have more doubts, please let me know. So these are called convolutional neural networks because there are some convolutional layers where filters, in this case of size 6 times 6, pass through the images, and you convolve the image where the input is the flux normalized. You convolve that with the kernel here, and the values of the kernel, or what we also know as weights, is exactly what the machine wants to learn, okay? So in this first part, we have 3,488 free parameters already in the first layer. Then we also have another convolutional layer with max pooling, which basically chooses the maximum value, and this helps you to reduce your dimensions, otherwise the problem becomes too complex. And there's another concept which is called dropout, which basically you remove 25% of your weights, and this is very useful to avoid your model learning by heart your examples. Okay, because finally, so these are the convolutional layers. And finally, we have what is known as the flattening, which transform all these tensor-shaped arrays into just a vector. And then here we have the traditional fully connected convolutional layer, where each of these neurons would be connected to each of the neurons with a particular set of weights. And the final output is one value, which in the case of a binary classification would be the probability of being a positive example. And in the case of the regression mode would be just the parameter that you want to guess. So as I said before, you see that this is a very complex mathematical function with a lot of free parameters, and the dropout that I mentioned before helps to reduce this number of parameters so that your model does not memorize your examples and is able to generalize. So when it sees an example that has never passed through the machine, it's able to do accurate predictions. Okay, so in this first paper, we use this convolutional neural network to classify images from the SDSS survey, the Slow and Digital Sky Survey, which has sampled 1/3 of the sky with multi-deep color band surveys with this Apache Point Observatory. So, because as I said before, what we use is supervised deep learning, we need to have classes or labels for the galaxies that we want to classify. And that is where we use the galaxy subclassification scheme, which was an excellent catalog for labeling our galaxies so that our models were able to learn from them. This consists in 240,000 galaxies, as I said before, classified by amateur astronomers. And note here the low redshift and bright magnitude N, and I will go back to this in the fourth part of the talk. So as a training methodology, the Galaxy Zoo has different questions. There's a decision tree, so depending on the previous answer, you go from one branch to the other branch. And what we did was to, instead of trying to reproduce the full tree at the same time, we took each question and trained it separately in a binary mode. And instead of using all the galaxies, we only used those that had an agreement between classifiers larger than 0.3. This is a mathematical quantity that I can explain you later. I don't have time to go into the details. And we also required to have at least votes. In this sense, what we want to say is that we use a robust training sample. We prefer to have a smaller training sample, but for which the classifications were certain. And one of the first questions is to separate the smooth galaxies versus galaxies with disk and features, for example. How do we test the performance of the models? I'm going to explain the ROC curve. Since we are not so many, if many of you already know what it is, maybe I can skip this part. If I don't hear anything, I will keep on. But if you all know what it is, maybe we can move on. So in a binary mode, you have your input, your actual class, which would be positive or negative, and your predicted class, which will be again negative or yes or no. So you can divide your sample into true positives and true negatives, but also false positives and false negatives. And therefore, with these numbers, you can derive the accuracy, which is the fraction of correctly classified samples over your full sample. The true positive rate, which is the fraction of true positives versus the positive. The false positive rate, which is the fraction of false positives versus the negatives. And the precision, which is of all the positives returned by your model, how many of them are true. So you can assign you can explain the true positive rate is something similar to the completeness, and the precision would be a measurement of the contamination. Okay, so then to plot the ROC curve, you need, so basically the ROC curve represents the true positive rate versus the false positive rate for different thresholds, okay? And let me explain this better, what the threshold means. Imagine that we have here this sample over here, where these are positive examples and these are negative examples. And we say, okay, my threshold to consider a positive example will be 0. Then you will recover all your positives, so your true positive rate, will be 1, but your false positive rate will also be 1 because you will be classifying all your or your negatives as positives. So your point will be in the 1, 1. If you increase the threshold a little bit more, you are a little bit more restrictive, then you start classifying as negative the negatives, which is good, but you also start missing some of the positives. And we do this until we reach to the end, where we have exactly the opposite situation, where we classify everything as negative. So the false positive rate and the true negative rate are 0, 0. And this is what is known as the REOC curve. So basically, if you have you want to maximize the area under the curve, this would be like a very nice separation. This would be reasonable, some poor separation, and something which is random would be something along the diagonal line. So let me show our ROC curves for the first of the models. This is for the Sloan sample, separating smooth versus these galaxies, and you can see how nice this ROC curve behaves, very close to the upper left column as we want, with an accuracy as high as 98%. We did that for other classification tasks, such as identifying edge-on galaxies or the presence of a bar. As you can see here, the accuracies in all the cases are very, very large. So the results are very, very good. And so you can trust me, I will show you some examples of galaxies which are classified as these galaxies, also to call you a little bit of attention. If you lose the interest in the talk, please look at these beautiful images where you can see these very nice spiral galaxies. Some of them are edge-on, they're pretty cool. For the edge-on sample, it's also very, very successful. It identifies very easily the edge-on galaxies that you can see here. And what it was a little bit more tricky was to classify galaxies according to the presence of the bar. So the model is not so accurate and so fine, but still you can see here that we are able to identify a lot of barred galaxies, which has also a lot of importance for evolutionary studies. Okay, so this was done with the Galaxy Zoo morphological classification, but we wanted to push a little bit higher. We wanted to assign a T-type to each of the galaxy. And in order to do so, we needed a reference catalog. And in this case, we used the NIRE catalog, which contains 14,000 galaxies, which were classified by a professional, Preeti Nair, who I have the pleasure to know. And it was, she can tell you that it was a very tough work. Again, note here the very bright magnitude limit. And this catalog provides, as long apart from a T-type, the presence of bar, ring, lenses, tails, and etc. So what we did in this case is using a very similar convolutional neural network architecture, but we trained the model in regression mode. So now the output of the galaxy, of the model, is not a probability, but it's directly the T-type of the galaxy. So you can directly compare the output type with the input T-type. And you can see how there's a very nice one-to-one relation with a little bit of scatter, but this is something normal, and actually it happens when you classify galaxies by eye. And in fact, we obtain a scatter which is smaller than the one obtained by previous work, and similar to the scatter that you will obtain with a visual classification, which is of the order of one T-type. Here again, some images of the galaxies ordered by T-type. So you start with very roundish elliptical objects. Then you start having some elliptic lenticular ones with the bulge and the disc, but no spiral arms. And then the spiral arms start to appear, and we have also edge-on galaxies. So the T-type model works. But if you look at this plot, you will see that the one-to-one relation breaks at the high and low T-type end. This there's not much to do because the statistic is very low. There are not so many very late type galaxies. But here we have a lot of examples. And the problem is that the model is trying to learn all these classes, and it's having difficulties between distinguishing ellipticals from lenticulars. And therefore, we decided to train an additional model. In this case, it was a binary model. So we try to separate ellipticals from lenticular galaxies. And this is the probability of being lenticular galaxy. And you can see how well this model separates the pure elliptical population from the lenticular or SA population. While for these intermediate ones, the probabilities spread all over the intermediate probabilities as expected. So this is an additional classification which is useful for any analysis. For example, with Giuseppos and Josep Maria, we are using this classification for analyzing manga lenticular galaxies. So the final catalog contains 607,000 galaxies. This is 3 times larger than the Galaxy Zoo catalog. It's really much faster, and I'm going to talk about this very soon. It has robust classification and includes the T-type and the separation between ellipticals and lenticular, which is something that I had never done before. And when I say this is very fast, the good thing about these models is that once they are trained, then you're done. You can classify any new galaxy coming from the same data domain relatively fast. So we use the same exact models to classify the manga galaxies because the manga observation, well, for those of you who don't know, manga is an integral field spectroscopic survey, which will observe 10,000 galaxies. But the images of the galaxies come from the Sloan telescope. So we were able to just take the models, apply them to the new manga sample, and we have the morphological catalog, which was released with the manga data release as a value-added catalog with its companion paper containing pi morphometric parameters, which were presented in the paper Fisher, Domínguez, Sánchez, and Bernardi in 2019. So in this work, we were able to do very cool things like combining morphology and kinematics. I don't have time to go into the detail, but here I show the angular momentum versus ellipticity for galaxies color-coded according to our morphological classification. And you can see that there are very nice correlations, even though the kinematics had nothing to do into the morphological classification. And we also tested how the Galaxy Zoo classification compares to our classification. And we found something which is, I think it's relevant for any science being done with the Galaxy Zoo catalogs. We found that if you use the probability of being smooth from the Galaxy Zoo to select your sample of early type galaxies, if you make a cut at 0.6, you have a contribution of late type galaxies, the blue and the green lines, as high as a 40%, okay? And because we had the photometric parameters, we were able to see what are the properties of these galaxies, for example, the Sérsic index or the B/T. And we saw that for the things that we call late type galaxies, even though they have a probability of being smooth larger than 0.6, these are galaxies with very low Sérsic index. So they are no elliptical galaxies. And you can see the same with the bulge over total is not so evident. The separation is not so clear, but it's very nice in here. And what is happening here is not that the galaxy zoo is wrong, is that, in my opinion, the question was not very clearly redacted. The galaxy zoo question says, is the galaxy smooth with no signs of a disk? And for an amateur astronomer, you as an astronomer would expect to separate early type or ellipticals versus late type or spirals. But an amateur astronomer sees a galaxy like this, and does it has the presence of a disk or a spiral arms? No. So these are the example of galaxies which are have a high probability of being smooth, but they are no early type galaxies at all. So be careful when trying to select an early type sample using this galaxy zoo question. Okay, let me check my time. Okay, so far so good. Models work very well. They are very fast, they are very accurate, but we need to have pre-labeled samples because this is supervised learning. We need to have catalogs with classifications for galaxies. And the problem is that the models, yes, so the supervised deep learning algorithms rely on training samples which need to have at least 5,000 or even 10,000 labeled galaxies depending on the question. So the key question was if we will be able to recycle the features learned by one survey to another. So how much of the knowledge acquired from an existing survey can be exported to a new data set. And this is because each instrument has its own characteristics like scene, PSF effect, pixel size, etc. So when you go and apply the models learned by the Sloan images, and you try to classify other images, like for example, the dark energy survey, the models don't work fine, and I will show you in a minute. So in this case, we wanted to transfer the knowledge that we had learned from our training in the Sloan survey to the dark energy survey, where the dark energy survey, it's an international collaborative effort to prove the origin of the accelerated universe. But as a byproduct, it will observe 300 million galaxies. So we really need to automatize the classification of these galaxies. So as I said, if we in this plot, what I saw is the ROC curve for the model trained with the Sloan galaxies and applied to Sloan galaxies. And this is the blue line here, which has a very nice behavior. So if you take this model, so exactly the same set of weights, the same mathematical function, and apply it to a sample of DS galaxies, so the photometry, the images come from the DS survey, the models don't work well. They are affected by these differences between different instrumentation, which are not optimized for this survey. So what we tested was instead of retraining the model from scratch, because we didn't have so many labeled galaxies from the dark energy survey, we did what is known as the transfer learning. So our starting point for the weights was not random, but rather the weights that had been learned by the Sloan survey. And now, by using only 500 galaxies as a training sample, we were able to reach similar values, comparable values to the ones that we obtained using 5,000 galaxies as a training sample. So we did the same thing for the Ed-John and the Bars model, and you can see exactly the same behavior for all cases. We reach very high accuracies with a very small number of training samples. And so we conclude that recycling the features and weights learned from different samples helps reducing the training sample by 1 order of magnitude. And this is going to be crucial in order to obtain morphologies or even any other kind of supervised deep learning algorithm from one survey to another. We won't need to classify by hand all these galaxies. We can rely on what we have learned from other surveys and then do this fast adaptation step. And this is the fourth part of my talk. So what I have shown so far is restricted to very bright galaxies. But the interesting things, what we are interested in for galaxy evolution, happens at high redshift and therefore for faint galaxies. So how can we classify these galaxies? So the first thing that happens is that the catalogs that we have with the labels, they are limited to bright galaxies, as I saw you before, lower than 17 magnitudes. So we need to have a sample of labeled galaxies, but if we look at these galaxies by eye, they're very blurry and they're very difficult to classify by eye. So we come out with this idea that we present in a paper which has already been submitted to the journal. They don't find a referee, so if any of you wants to be the referee of the paper, please contact us. And where we try to push the morphological classification to their limits for the dark energy survey. So what our approach was the following. We have local galaxies, low redshift galaxies with well-known morphological classifications, because these come from the overlap with the Sloan catalogue and the dark energy survey. And so these are original dark energy survey images. They have the effect of PSF, seeing, etc., etc. And we simulate how these galaxies look like at fainter magnitudes by applying the cosmological dimming, both in flux and size, K-correction plus evolution effects, and we deconvolve by the PSF, add noise, and then reconvolve by the PSF. And this is how the galaxies look like at different magnitudes. So you can see that when you go to the fainter magnitudes, it's really difficult to distinguish these two objects, which were very different in the local universe. So what we did was to keep the labels that we know were the truth, but now using the simulated classifications. And we wanted to test if the machines were able to recover these features, which apparently are hidden to the human eye. A human would have a lot of difficulties to distinguish between, to say if this is a spiral or an elliptical galaxy. Okay, so we did our training sample by using the original, what we know as the primary training sample, which are the original galaxies limited to magnitudes fainter than 18, with their original labels. And then we did two sets of simulations, one which were random up to magnitude 22.5, and the second one, which was the maximum redshift we could push the galaxy as long as it was brighter than.
Sorry, Helena,
yes?
we have 5 minutes left.
Okay, I'm almost done, so I think I will make it on time. So to the higher redshift where we could reach, given the magnitude and the size limits, okay? And this is the test sample. And we train, in this case, we cannot go so fine as the T-type, so we just divided galaxies into early type and late type, and also edge-on versus face-on. So here I show you the ROC curves for these models. In this case, we use a scaffolding with 5 different training sets because we had enough data. And by using these 4 different models, we can also try to measure somehow the uncertainties. If the 5 models are in very good agreement, then we assume that this is a certain classification, while if the differences are largest, then we think that this is a more uncertain classification. So you see here the nice ROC curves, very nice confusion matrix, reaching 96 and 97%. But we wanted to test if the results were affected by the observed magnitudes. So we divided our sample into magnitude bins, and we derive all these quantities, the area under the curve, the precision, the recall, and the accuracy. And we see almost no trend with magnitude, or no clear trend. And please note how high these axes are. They're never below 22%. So we conclude that the machines were able to recover the features which are actually hidden to the human eye. We did the same with the edge-on. Just quickly showing you the results. Again, there's no clear trend with magnitude. So we were very happy, but So far, what I've shown is tested on the same set of simulations that were used for training. So we wanted to know how our models behave on real galaxies. And in order to do so, we compile all the information available in the dark energy survey. This is the distribution in magnitude of our morphological catalog. This is the Tarsitano catalog with structural parameters. These are the mass and photometric redshift catalog. And finally, this is the Vipers spectroscopic sample that please note that remember later that this is the faintest sample of all. So when we compare the absolute magnitude versus the spectroscopic redshift for our classification, the predictive fraction is 1 if the galaxies are spiral and 0 if they're early type. We see there's a very nice separation between the two. And as expected, the early type galaxies are the brightest at each redshift. We did the same for the ellipticity, Sérsic index and radius. And you can see here how galaxies with a high Sérsic index are always classified as ellipticals, except if they have high ellipticity. And here again, these are galaxies classified as edge-on or face-on, and you can see that there is a very nice cut with ellipticity. These are some numbers. Just 96% of early type galaxies have high Sérsic index. 99% of edge-on galaxies have high ellipticities. And finally, and this is one of my favorite plots, this is the comparison of our morphological classes with the spectral classes from the Vipers spectral classification. So this classification, dividing galaxies into passive, intermediate, and star forming, are derived by the spectra of the galaxies. And look how well our morphological classification, coming only from photometry, correlate with these three classes. And also remember that this is the faintest sample of our morphological catalog. So we have created this catalog, which contains 27 million galaxies, reaching magnitudes as faint as 21.5. And this will be released with the paper. And I'm very proud to say that this is the largest morphological catalog up to date. So please come and use it. It's going to be a great tool for galaxy evolution studies. And as an epilogue, I will just like to briefly mention, because I think I'm out of time right now, which are the projects that I'm involved in right now using deep learning. So for example, we are deriving the morphological classification for the final manga data release, which will contain 10,000 galaxies. I'm also collaborating on a project to identify galaxy lensing in JPass, the detection of low surface brightness structures with hypersubaru CAM, the use of generative adversarial networks to generate galaxies from different samples, and also the pixel level classification using the code of Morpheus with collaborators from California. And especially for the three last projects, collaboration is needed. Collaboration is welcome. So if you're interested in any of these projects and to work with me, please come and ask me. And if you have any questions, here I am, and this is my email if you prefer to contact me by email.
Okay, thank you very much, Helena, for this very nice talk. Now we have time for a few questions and comments, and this part will be supervised by Jose Luis. And he has me to tell you that in order to participate, please, instead of clicking the raise your hand icon, write a Q on the chat. It will be better for controlling the participation. So please go ahead.
Okay. Well, in first place, thank you very much, Helena, for this super nice talk. And just to say you that I can't wait to use this catalog. So I hope it's released very soon. The first question comes from Vishal. So Vishal, please, you want to...
Yeah. I sort of have my questions typed. So if you don't mind, can I type it on the chat widget? If I can paste it.
Yeah, sure.
I have a few questions together.
Are you gonna read it, or do you want me to?
Yeah, I can read. Yeah.
Okay.
So first of all, I've been personally trying to use deep learning in image classification, and I've been looking at Zooniverse datasets. So one of the datasets which I looked at is SuperVASP, basically variable stars, and they don't have distinct morphological features such as galaxies. They're more of time series plots. So I have the link pasted here. So you think deep learning is feasible in such cases?
Yes, yes, indeed. Yeah. Do you prefer to post all the questions and I reply to all of them?
Yeah, yeah. And secondly, since it's like quite cumbersome going through millions of images, what would be the scope for unsupervised learning, especially with state-of-the-art models that's available? And thirdly, with data sets generated from telescopes, there seems to be a lot of false data or noisy data. And if at all we use deep learning, wouldn't that result in inaccurate classifications in the longer run?
Thank you, Vishal. Actually, all of your 3 questions are very interesting. So the first one, you're right. If you have something like a time series or a spectra where you only have 1 dimension, then you would think you cannot use deep learning. But actually, you can use convolutional models in 1 dimension. So you can still use your input will be a vector now instead of an array, and you can use 1D convolutional layers, and it will extract the features, and then you can use it in a similar way as for the galaxy morphologies. And in fact, I know this has been done for determining, for example, star formation histories in simulations from spectra, but also, for example, to identify X-ray X-ray pulsars and other time series variable objects. Regarding the use of unsupervised learning, well, unsupervised learning is really, really, really interesting, and it's the future of the deep learning models. In the astronomical meeting of the Spanish Society, I was very proudly invited to give a talk with Mark, where we presented the state of the art of the machine learning applied to astronomy. And in the second part of the talk, Mark talked a lot about the unsupervised learning, which, if you want to compare it with a cake, the supervised learning would be the icing of the cake, while the whole, the real cake will be the unsupervised. And this is because it will allow us to find things that we didn't even know we were wanting to find. So the supervised learning has the advantage of the models will learn what you want them to learn, but then you have to assume what it is that is important that you want them to learn. So unsupervised is going to be super powerful and super useful, and I know some pieces of work which already exploded this for morphological classification of galaxies, and they're very nice. And finally, regarding the noisy data or false data, also deep learning can help in this. And for example, there are also a lot of projects which identify what are known, I'm trying to think about the word, it's not coming to my mind, but basically what they do is they look for the distribution of the inputs, and then galaxies or objects which don't fall into that distribution, they're identified as potential interest. And if you go and look at them, many of them are this noisy data or false data, so you can use these distributions to remove artifacts, but also to find interesting objects. And I hope I have answered the 3 questions.
Yeah, thank you so much.
All right, thank you. Now we have a question from Ricardo Perez. Go ahead, please.
Hi, Helena. First of all, nice to meet you, even this virtual shape. Very nice talk. I enjoyed it a lot. Well, one of my question is, you said that you are able to apply what you got from SDSS into DSS, into this dark energy survey with some transformation. The transformation is related to the telescope and camera, I mean, to the instrumental setup, or is there any factor in like exposure times or dither or something else?
So I think it's a combination of everything. And the truth is that so the supervised deep learning is very powerful, but it's also very unknown. It's kind of a black box. So we don't really know what is it learning from the models. So we don't exactly know what is affecting it so that it doesn't work so well in other surveys. So we believe it's a combination of everything. Definitely PSF, definitely maybe pixel size, the way the galaxies are normalized, even the different color ranges. This is something that I always wanted to investigate in deeper detail, but it's really, really difficult to try to understand what is going on. But definitely another thing that it's very important is the magnitude or the depth of the surveys, right? And for example, one of the challenges that we are going to face when telescopes like LSST will come is that these are going to be super deep. We're going to have a lot of background objects, and the models that we are using so far will not be valid. So we need to validate them, for example, with simulations. But then again, simulations have to be super well calibrated to take into account every observational caveats, because otherwise, if you train your models with simulations and you forget, or your simulations are not perfectly don't perfectly resemble the real observations, then your models are going to be affected. But yeah, so there are many characteristics that can affect your models, and it's difficult to exactly assess how each of them contribute to the uncertainties.
Okay, thank you.
Okay, let's see if there is more questions. If you want, if you prefer, you can just write the question in the chat, and I could also...
Okay, I have a question in the meantime. Have you, Helena, applied or do you intend to apply your methodology to other classification schemes? I'm thinking, for instance, in the CAS, the concentration, asymmetry, and smoothness classification system, which is relatively simple and also relies on the structure of galaxies as Hubbles. But what for me is most important, it is fully objective. Okay, and this would perhaps avoid the problem of or the caveat of this training sample dependence of the network neural network based methodology.
So you mean to have a model which determines the CAS, or to
no? Well, if you have considered to use other classification schemes that Hubbles. I mean, basically what you are doing is apply Hubbles or T-type, which is an evolution of Hubbles. Okay, but another scheme which is not strictly. My worry about Hubbles is that it is intended for nearby galaxies in the local volume, which are very bright, and not necessarily the galaxies like of the dark energy survey. Really, although you have applied these corrections, okay, not just instrumental corrections, but also evolutionary correction. But I'm not very sure that actually you can extrapolate. as you mentioned, you realize that you couldn't apply the T-type classification, and you have to only deal with disk and spheroids. Okay, so maybe another classification scheme will be more suitable. So yeah. Starting from a different point, okay, not a Hubble classification system, but I'm not especially a fan of CAS. I mentioned I mentioned this scheme because it is objective, okay, and so everybody should agree on the outcome of this classification, and this doesn't happen with Hubble's.
So you're totally right that the Hubble classification is based on local galaxies, and in fact, we don't really know which shapes distant galaxies have, so this is a simplification. And there are two things you can do. One is to use unsupervised learning, as we mentioned before. Then the model itself will find the different structures that you can observe in the high universe. And also, in fact, I hadn't thought about using the CAS as a predicted value, but you can definitely do that. I think it will be relatively easy for the model to learn that because this is something quantitative. So it will be relatively simple to measure it from a mathematical function, which at the end is the CNN. And in my opinion, I think it will be easier than measuring a Hubble sequence that, as you say, is somehow subjective, right? So I think it's a good idea, and it can be easily done, and I think it's doable and can be useful. Yeah.
Thank you.
All right, I think we have time for one or two questions more. Well, since I don't see any, I will ask you something, Helena, if you let me.
Sure.
I think that in the catalog of Nair and Abrahams, apart from this t-type and the presence of bar, they also provided well, a parameter indicating the presence of other fine structure like rings, lenses, and warps.
Mm-hmm.
Have you ever considered finding them with your neural networks? That would be very cool to have it for the entire SDSS.
Yes, we tried. The problem is that there are very few positive examples. Rings, lenses, and this kind of things are very rare. So it was already very difficult for us to train the presence of a bar model, and the fraction of objects that have rings or arcs are even smaller. So we tried, but the training sample is really unbalanced. The features are very, very faint. And at the end, we didn't have good enough results to make them public. So yeah, we tried. There can be turnarounds, but yeah, it's not so straightforward.
Okay, what a pity.
Yeah, we can try. We can try again.
All right. So if there are, yeah, we have another question from Celsa Pardo.
Please, I have a question actually. You did speak about unsupervised methods, but have you ever applied some of the unsupervised method that we already have with this data, or you even tried?
So myself personally, I have never worked with unsupervised. My experience so far is with supervised learning, but my collaborators have, and I know of very nice works. For example, there's a Cheng 2019 or 20 that does the morphological classification for dark energy survey using unsupervised learning and finds very, very cool things. And also, for example, if when I do the comparison with the Viper's spectroscopical classification, that classification comes from an unsupervised analysis of the spectra.
Okay, thanks.
But the short question is, the short answer is no, I haven't tried it myself.
Okay, thanks.
Okay, then thank you very much. I think time is up. Okay, so I thank again Helena for his talk and all the people attending this seminar. I hope we can see you soon again.